you ready?
Yes.
All right. Our next talk is by Roberto Miatello. And he will tell us about generalized Poincaré series for SU21. You have the floor.
Okay, first of all, I would like to thank the organizers for the invitation. I will speak on Poincaré series. That is a subject that goes back to Poincaré. So in the study of automorphic forms, so the idea is just to take a function h on a space x, that could be the upper half plane, and to form the sum of the function, a sum of transformed functions, h, the sum of h gamma x. And then if this converges, we get a gamma invariant function. And Poincaré constructed in this way what he called fonction theta fuchsienne. So I am just giving some history of the subject. And in the theory of holomorphic automorphic forms, one uses the germ h of z to e to 2 pi n z on the upper half plane that is invariant under the transformation, the translation z in z plus 1, and then it leads to a series that converges absolutely, and now the sum has to be over SL2z mod gamma infinity, because this function is gamma infinity invariant. Gamma infinity is generated by this upper triangular matrix. So the resulting series sometimes is 0, but they are important because later Hecke and Peterson, they showed that these series span the spaces of holomorphic cusforms. Then the subject went on with Maas and Zellberg in the study of the so-called real analytic Eisenstein series. They used the same idea for a function h sub s of x plus I y in the upper half plane, given by that formula that you can read. The I function is an I Bessel function, is exponentially increasing modified Bessel function. And then this function is an eigenfunction of the Laplace operator on the upper half plane. Then when we sum, we get an eigenfunction of the Laplace operator. So we get what is now not a holomorphic, but a real analytic form with exponential growth that is at the same time an eigenfunction of the Laplacian. So these are so-called real analytic Poincaré series, and it is a family depending on S, initially defined on a right half plane, and then they accept a meromorphic continuation to a complex plane. And Neunhofer and Niebuhr, independently, they showed that the mass cusforms are spanned by the residues of these families. So these families are important in that sense. Then now all this can be translated into functions on the group SL2R, since the upper half plane is just a quotient of SL2R by the orthogonal group. So then we get functions that satisfy transformation rules relative to the subgroup K, and also relative to the discrete subgroup gamma of G. So this is the subject of the book by Lang, SL2R. Now, jointly with Nolan Wallach, we worked on this subject by extending the methods to automorphic forms on arbitrarily groups of rank 1. For instance, SON1, SUN1. Then we take gamma, a discrete subgroup of G of finite covolume, when we use a holomorphic family of germs, H, of Casimir eigenfunctions, with the property that H of NG is transforms by a character, unitary character of the subgroup N, is a unipotent subgroup. It's a maximal unipotent subgroup that is trivial on the intersection of N with K. So we proved that there is a meromorphic continuation and a functional equation, and the residues at singularities are square integrable automorphic forms. So the main idea here is that the functions we sum are good at the identity, but they grow a lot at infinity. They are not of moderate growth. They are not automorphic forms. But one works with a family of exponentially increasing forms, and then after continuation, and when one takes the residues do give square integrable automorphic forms. So that's the use. So in many cases, these Cas forms are spanned by residues of these Poincare series. On the other hand, some important automorphic forms cannot be reached by our residues because they are the so-called non-generic Cas forms. They turn to have all their chi Fourier coefficients equal to 0 for all characters chi. The Fourier expansion is more complicated and requires representations that are not one-dimensional. It requires infinite dimensional representations of the group, of the unipotent group N. So such Cas forms cannot be detected but by our series. So these Cas forms corresponds to representations that do not have Whittaker models. And the work of Constant and Vaughan, they give algebraic conditions so that a representation doesn't have such a model. In general, discrete series, holomorphic discrete series, or other similar representations do not admit. So then, jointly with Rudolf Brueggemann, we took the case of the group SU21. It's a small group, but already it has a unipotent group that is a Heisenberg group that has infinite dimensional representations of N. So we defined the family that we call non-abelian Poincare series. So these are Poincare series that are attached to Stone von Neumann representations of the unipotent subgroup N. So then we prove that there is a meromorphic continuation to C and that the residues at the poles are square integrable automorphic forms. And then we compute the inner product of any square integral automorphic forms with truncations of this series in connection with the Fourier expansion. And as a consequence, we obtain general completeness results that generalize those for the classical holomorphic and anti-holomorphic Poincare series for SL2R, and that also complete the work in rank 1 for this particular group, relative that we can reach all representations this way. So this is more or less a summary of the talk, and now we have to get into the work. So So here is the group SU21 is inside SL3C is a bunch of matrices satisfying this identity, 2.1. Then, as all semi-simple groups, G has an Iwasawa decomposition, N times A times K, where N is nilpotent, A is abelian, K is compact. This is G is diffeomorphic to this product, diffeomorphic to the product, but of course it's not isomorphic because G is a simple group, so these subgroups are not normal, but every element of G can be written as a product of NAK in a unique way. So K is the compact group, is just U2, is this type of matrices, like 2, 2. So delta is the inverse of determinant. It's a maximal compact subgroup. Then we have A is an abelian subgroup, is just is the identity component of split torus. And then the unipotent subgroup N, that is very important for us, is isomorphic to the Heisenberg group on R2. The center, so it's parameterized by B and R, where B is in C and R is in R. So now we have to describe some of the ingredients. So irreducible representations of K are just representations of SU2 and a character on U1, and they have to satisfy some compatibility condition. Then the irreducible representations tau P of SU2 are classified by their dimension. And then we extend to U2, like in 2.4. And then, well, we get representations that we call tau P P plus 1. Then we need lattices on N, in N. So if gamma is a lattice in G, then the intersection with N is a lattice in N. So it's a discrete subgroup with compact comotion. So every lattice in N is isomorphic to what we call a standard lattice. So at least for this work, we'll work with lattices of this type. So these lattices have the property that they have only one cusp. So lambda sigma satisfies those conditions. B is in Z of I, and R is of the form 2 mod sigma times an integer. So now we have to study the decomposition of N mod lambda sigma. This is a compact space. Lambda sigma is not normal in N. This is just a quotient. Then we have a Haar measure here, and we look at the irreducible representations of N. The center acts by a central character for any irreducible representation. So if the central character is trivial, then the representations corresponds to representations of the quotient R2, hence is a character of N. But if the Haar character is non-trivial, then we come into the so-called, if the center acts by N0R e to the R lambda for lambda non-zero, so there is only one isomorphism class of irreducible representations of N with such central character. It's unitary, and it's called the Stone-von-Neumann representation. So one can realize it on functions on L2 of R, and then with the action given by 2,7. And so if phi is a Schwartz function on R, then that is the action. For the standard inner product in L2 of R. Now we get into theta functions. We can transfer this representation into L2 of n mod lambda sigma by means of theta functions. So the theta functions for any Schwartz functions phi on R, theta LC is given by that formula, 2.8. So this gives 2 times L realizations orthogonal inside L2 n mod of the representation. So then now we have to choose phi, and there a basis of L2 of R is orthogonal basis is the normalized Hermite functions. So we plug them into the theta functions, and then we get finally an orthogonal basis of L2 of n mod lambda sigma. So the orthogonal basis is partly characters, chi beta, and partly theta functions with Hermite functions in them. So now we can go into Fourier expansions. So using the basis B, we can get a generalized Fourier expansion. So we have 3.1. So any f can be expanded in that way. With B an element in the base. And now we have a Fourier term operator that we call f sub beta is that integral. So these are chi beta equivariant under left translations by elements of n. So the abelian part of the Fourier expansion is a sum of f beta f of G with beta in Z of I. So this is the abelian part. So we get an intertwining operator for the action of the Lie algebra by right differentiation. Now, relative to the non-abelian part, that is the complicated one, so the action of the Lie algebra does not preserve individual terms, but we can group them conveniently. So we get operators F sub LCD that involves combinations of the theta functions, suitable combinations. So we get the Fourier terms relative of the function f relative to each element of the basis of the basis of L2n mod lambda sigma. So if we sum, now we call these terms, we call f sub nf. Well, n now will denote these the letters LCD, and this is the non-abelian part of the Fourier expansion. So then we denote by calligraphic n a realization of a representation of n in C infinity of n mod lambda sigma. So is the index in the Fourier expansion. So it involves f sub beta for beta a character, a unitary character, or f sub n, f of LCD, when we have a Stone-von-Neumann representation. So these we call Fourier term modules. So inside there, we have submodules where the center of the universal enveloping algebra acts according to a character. So then we need the functions that are determined by the boundary behavior. So we have exponentially decreasing functions at infinity, and we have functions that grow at infinity and are good at the identity. So this involves the differential equations involved. So then these spaces, we have in general, the idea is that we fix for abelian Fourier term modules, we have a part that is a W and a part that is M. So this is like an M is like the I Bessel function, and W is like the K Bessel function. So the K Bessel function is good at decreases at infinity, and the I Bessel function grows at infinity, but it's good at the identity. So this is the main idea. So then we have any function on this space is a sum of one of these, and then the idea is that here is the formula. You see, these are functions of n, a, k. Any element in the group G can be written in this way. So it has a character of n, chi beta, then a function of a of t, a function of the abelian part, and then a k-type. The k-type is a function on a compact group, so does not matter very much. In the case of non-abelian Fourier term modules, these expressions are much more involved. Okay. So now we go into automorphic forms. So we want to study automorphic forms for gamma in the group SU21. So an automorphic form is the standard definition, is gamma invariant on the left and K finite on the right. It is an eigenfunction of the center of the enveloping algebra, and it has polynomial growth at the identity. So it doesn't grow too much. And the space of automorphic forms, we call it A of psi, where psi is the character of the center of the universal enveloping algebra acting. Then when we put subindexes HP, it means that there is a K-type tau. And then we also need a space of rapidly increasing automorphic forms that we call moderate exponential growth if they have only finitely many increasing Fourier coefficients. So these are important for our results. Then we have Haar measures on N, A, and K. We use a measure on K that gives it volume 1. When we have an inner product on L2 Gmod gamma, and then we can decompose the space of square integral automorphic forms with character psi as orthogonal direct sum of finitely many reducible modules, all of the same type. And for any f here, we have an absolutely convergent Fourier expansion. And f of g is equal to 4.3. So this is the Fourier term expansion of the kinds that we just described, involving characters of n and representations. So this is the equivalent for a Fourier series. This would be like e to the int and the standard expansion of a function. But in this case, for the Heisenberg group, or for SU21, this is much more involved. So now we go into Poincaré series. So we take a function on G mod gamma intersection n, and then with some growth conditions, and then one can do the Poincaré thing, that is take the summit over gamma, mod gamma n, and then the first basic example is the Einstein series. The Einstein series is also Poincaré series, but we start with a function that is invariant on the left by n. So then it's an easy function. It doesn't mean the Einstein series are easy, but they are well known now. The meromorphic continuation was done by Selberg first, and then by Langlands in full generality. So the Einstein series are automorphic forms, and they converge for real part of nu greater than 2 and have a meromorphic continuation to C, and they are fundamental in the expansion of functions in L2 of G mod gamma for the continuous spectrum, right? So they play the role of the Fourier transform on Rn, say, in this context. So now so the idea is that what we want to sum is a function that has a certain growth as t tends to 0. So that is the business of automorphic Poincaré series, that we need to use as a function one of those functions in the subspace of type M sub n. So then the result is that we need some non-zero meromorphic families M sub n for each Fourier term order. The Fourier term orders, remember, are just involve characters of n or representations. So for each, we can construct some meromorphic families of functions on G mod gamma n with some properties, that the function is meromorphic in C with at most first order singularities in a discrete set of points in Z in the negative integers, and then if it's holomorphic at nu, part B is that if it's holomorphic at nu naught, then the value is good. It's a function that is an automorphic form of moderate growth. Moderate exponential growth. Then if M has a singularity at a point, then it is a simple pole and the residue is good. It is an eigenfunction of the cousin. So the second fact that we need is that we take a Fourier term order, then for each function, we can form the Poincaré series, and then we call this bold M sub n. So this is a well-defined element with moderate exponential growth for real part of nu greater than 2. So the family is holomorphic for real part of nu greater than 2, and then it satisfies, it commutes with the action of the Lie algebra. And the Fourier terms are holomorphic families of elements, and then in the abelian case, they belong to the W space, and in non-abelian case, well, in the non-abelian case, they belong, in both cases, they belong mostly to the W space, except for finitely many indices.
Roberto,
Then the thing,
I'm
please.
sorry, before you continue, the time is up. We need to go on. I'm so sorry.
Can you try to summarize it, maybe
Yes,
Yeah.
I'm
another minute or
almost
so?
done.
Okay.
Yeah, I can just say what's
Okay.
coming.
Thank you.
This Poincare series can be meromorphically continued, and if we resolve the poles of the Poincare series, we get square integrable automorphic forms, and these automorphic forms generate the whole space of cusp forms, or L2 of SU21 mod gamma, and that's it.
All right. Thank you very
That's
much.
the end of the story.
Thank you very much. Any questions from the audience? Maybe we can have a short question.